Hey guys, welcome to some more of our circular motion and gravitation unit here. Today we're going to talk about gravitation and some of the math problems and the mathematics that involve with that. But first off, remember Newton didn't necessarily invent gravity, but he rather invented a way to describe how things are attracted to each other. And so basically, if our PhET simulation was the concepts for how things orbit and rotate around each other, what we're talking about today is the mathematics and how they're related to each other. And so we have gravity is affected by the masses of objects and their distances apart, right? And so that's what Newton was pretty famous for. So Fg, we're going to call this the force of gravity. And it is proportional, we're going to say directly proportional, to two masses, m1, m2, the product of two masses. So basically, the larger the mass is, the greater the force of gravity is between the two objects. So the force of gravity between two people would be less than the force of gravity between a planet and the person, for example, okay? So if it's proportional between the two masses, that means it's got to be inversely proportional to the square of the distance between their centers of mass, or in other words, 1 over r squared. So it behaves like an inverse square law. And if we do a quick sketch of what that looks like, we're going to just stay in the positive part. If this is Fg, and this is... Oh, sorry. No, this would be the distance, the x squared, and this is the Fg. We see that as we get farther apart, the force of gravity gets really, really, really low. And as I get closer to the center, the force of gravity rises exponentially. So that's kind of leading us to how black holes work, and we'll talk about that later. But the main equation we're going to use, Newton's universal law of gravitation, looks something like this. Fg equals big G times m1 times m2 over r squared. And so we have this value big G, it's called the gravitational constant, and it is 6.67 times 10 to the negative 11th. And the units are kind of weird, as a Newton meter squared per kilogram squared. So back in Newton's day, they didn't know what it was, but we had ways to figure out later, and we can talk about that and look it up if you're interested in that later. M1 and M2 are the masses. So those could be planets, satellites, people, boats, whatever. Then the R is the distance between the centers of mass. And that's going to be really important, knowing it's the centers of mass that is going to be how we drive our problems here. So, pretty quick question here, quick example. Calculate the force of gravity between two 75-gram students, about 150 pounds each. The formula is Fg equals big G m1 m2 over r squared. Doesn't matter which one is m1 or m2. Gravitational constant is the 6.67 number. 75 squared, or just 75 times 75. And so these guys are about a meter apart, a little less. So this will be squared. When I run the calculation, we should get about 4.2 times 10 to the negative 7th newtons. And so this is the force of gravity between two people, about a meter apart. And this is obviously a very, very, very small number. Part of the thing about gravity is that it never stops. So things can be from one end of the universe to the other. They're always going to have some kind of gravitational pull on each other. It's just when the masses get really small or the distances get really, really big, the force of gravity is very small, so pretty much negligible in lots of cases. You'll see a lot of problems that are kind of behave like this. A satellite weighs 9,000 newtons on the surface. How much does it weigh if its mass is tripled and its orbital radius doubled? And so what we're asking is something like this. So if it's sitting on the Earth's surface, that's just like R1. So the force of gravity on 1, it's G m1 m2 over r squared, and we know that is 9,000 newtons. What it tells us is that the radius is now doubled, this is 2r, and the mass is tripled, 3m. The force of gravity for the second object is G m1, this is going to be 3 times m2, that's that second mass tripled, over 2r, this is doubled. So when I do the math on this, I get 3/4 big G m1 m2 over r squared. So if I look at this chunk here is going to be the same as this chunk here for those two pieces. So how much would it weigh if those things happened? Well, I'm just going to get my 3/4, multiply it by my previous 9,000 newtons that it weighed to get 6,750 newtons for how much it weighs if that doubles. So we'll have a lot of questions where things are tripled and the radius is doubled or what have you. So that's just how we handle those semi-conceptual questions where there's not tons of math involved. We're just understanding the inverse and the inverse and direct variation that happens in the equations. So when a satellite is in orbit, we've always heard that it's constantly falling, okay? But remember, it doesn't fall just towards the Earth, it falls around it. So an easy way to think of it is if there is a cannon that launches a cannonball, and here's Earth, if I launch it too slow, it would fall and just hit here, okay? If I launch it too fast, it would go away, probably curve a little bit because the gravity would pull it, but it would go too fast for the gravity to keep it glued together. So what we tend to think about is something is launched just enough to where it will start orbiting the Earth here. What happens is it falls down as much as it goes this way. So it's constantly being pushed just fast enough to not fall into the Earth, but it doesn't fall faster than that rate. So that's what we mean when something falls around the Earth. That's the reason you feel weightless. When you're in orbit, you're in constant free fall, but I have just enough of this tangential velocity here to keep me from falling into the planet because the gravity is pulling me in. So a quick example on how the centripetal force and acceleration match up with what we're doing here. We have a satellite orbiting the Earth at a certain radius, and we want to know what speed does it travel. So basically, here's what we have. Here's the Earth, there's the satellite, and that's the orbital radius. And so when it says orbital radius, it's giving me that whole distance. Sometimes we have to be careful to know that the radius of the Earth is something, and then it's a certain distance away. Just call that D for now. So just be aware that some questions involve us changing the radius just a little bit. But how we do this is pretty straightforward. We know that the centripetal force, this pulling in, is equal to the gravitational force that the satellite experiences. And so we saw a little bit of that with our simulation. So we have this idea here. So it's mass times centripetal acceleration equals the big formula for our gravitation, G m1 m2 over r squared. So my centripetal acceleration can turn into, let's call this m2 here. Mass 2 times v squared over r. That's my mass 2 is going to be my satellite here. And so what's happening is it's going this way at this tangential velocity here, and it is being pulled in by gravity, of course, okay? This is going to be equal to the same G m1 m2 over r squared. And what we see here are the M2s cancel. One of the R's cancel, leaving me with V squared equals G M1, mass of the Earth, over R. So we get an equation that looks something like this, 6.67 times 10 to the negative 11th. That's my big G. Mass of the Earth, 5.98 times 10 to the 24th kilograms. The distance, so the orbital radius that we're using here is 8.5 times 10 to the 7th. Take the radical of that, and so we get about 2,200 meters per second. And just for comparison purposes, this is about 4,920 miles per hour, just to give you an idea how fast things are actually orbiting when we put things up there. So anyway, that's gravitation. It's pretty quick, pretty straightforward. We'll have another one about gravitational fields. And once again, it's just this idea of how we envision gravity working. But you have a problem set for this, let me know how it goes and talk to you later. Thanks for watching. Bye.